And then validation also provided to another year. And I put, this is from the paper. I just drop it, put it here. The area 1 and 2 and 3 and time series plot for 5 years. And you see the green is original, and the blue is adjusted, and the red one is observation, so you improve that. And verification is provided to another different year, which is 2014. So you can see the improvements from the green and moving to the blue, and observation is red as a red. So that all the area are all improved from that correctly. And so it's pretty much to show you it's effective. And then the next part that I want to discuss with you is just a current continued improvement or in progress, which we want to use real-time gauge information as well to improve the estimate in the daily scale implementation. So pretty much the concept is this. Gauge has observation. Now we do have satellite adjust, gauge adjust the estimate, which you consider bias corrected. But we don't use the most current information, then we miss some kind of information if it is available. But of course, the gauge is available, then we can use it in near real time, then that would be wonderful. So for example, I put it say, okay, the right-hand side here is a 1 degree by 1 degree box with high resolution at 0.04 degree from our estimates. And gauge is over somewhere. So basically, over this free box could have two products. One is our bias corrected CCS estimate will cover the whole 1 degree by 1 degree with resolution 0.04. And the other part is a gauge estimate. But of course, a gauge can be interpolated into all the gauge or all the boxes with 0.042. So consider there are two products here. Then our estimates will put together, say, the merged estimate of satellite estimate and the gauge. So I put it here. It said I want to estimate this box, the green box, where they have our CCS adjust estimate, but of course also interpreted the gauge estimates here. So we're gonna have them put together in a merged product. So satellite estimates and gauge estimates as interpret the gauge estimate, then they combine together with a weighting factor. Okay, the weighting factor is a function of their uncertainty, which high uncertainty, would be with a lower weighting factor. So for the gauge location has if the pixel is under the gauge observation point, then we would assume that the gauge observation is good, and the point has a good observation. But if the point is out of the gauge observation, then the uncertainty is a function of distance away from the gauge location. So the far away distance will have much higher uncertainty. Of course, then we can use this kind of concept to build the uncertainty for the weighting factor, that we can come up with the combined estimates, which I put it into the merged estimates. So the weighting factor is inverse proportional to the uncertainty of the estimate from different sources, and the gauge with no uncertainty is small to mean square, then the gauge weight will be higher. So that would be a way to define for weighting factor when two products are put in together. So this is one way to do that, and we can calculate all the uncertainty according to the gauge and the distance out of the gauge, which is actually we are working on that for different papers at this time. So this is the result I quickly show you. Again, now the same kind of plots, say October, and we have gauge interpret the data over the left-hand side, and the original estimate CCS over the second second filter. And then the third one is the adjust the PERSIANN-CCS estimate. And the last one is the merge the estimate, include daily gauge and also include the adjust the PERSIANN estimate. So the scatter plots is over the right hand side. So you can see the red dot will be the merge the estimate, so which is pretty much along the 101 line over the area, which in general this study will exclude some of the gauge points, which also put it back later in order to show okay there are some verifications we can demonstrate. And then here is again two different zones. On the top one is okay. On the top one is okay. Yeah. And 1 second break. Is you correct? Put it back. Alright. So you got it right?
Yes, we got it.
You got it feedback? Okay, good. So now, good. So the green line on the top is the original estimates, and the adjust estimates in the blue line, and then the red one is the combined estimates. So and the observation now gauge is put it into the red line. So you will see the red line is more closer to the black line, and the merged estimates is improved one more. And then it's day-by-day correction, so that you can see in the middle panel that the time shift difference also can be corrected on the middle panel. And over the last time series plot, you can see again that the red and the black lines are very close together from this kind of merging. And we put it into the daily estimates for over 6-year period. So you can see the green one is every day, the overestimate over the top zone. And the adjusted is largely improved. Then the red one is even better. Of course, the correlation is pretty much like the one. And uncertainty reduced, bias reduced altogether over the period. And this is the bottom one with a really huge rainfall day by day over the distribution. Then you can also see the original one and then adjust the gauge adjust estimate and the merge the estimate in different parts. And then the red one actually is pretty much attached to the gauge, the black one over the time period. And again, this is a day-by-day accumulation plot for each year. So you can see the lines from the black one and this observation, and the line from the red one is the merged estimate in real time. So that basically you can see the improvements in general over the year. Okay, so that will pretty much conclude my presentation here. I'm sorry for the inconvenience because of the network connection issue. So, but we can have a short break, then we come back for close presentation, and then we can come back for the question and the answer part.